All right, this week we're getting into Module 5, and we cover a lot of things, but in particular we cover strings and how strings are compared to each other. Module 5, Section 7, it shows you how to compare strings using the comparison operators, same stuff that we used before. You get the equal to, not equal to, greater than, less than, and those comparison operators, those can be used to compare strings. But how does it do that? They're not numbers. So it shows you here. Let's say the first example is lowercase alpha is equal to lowercase alpha, and then lowercase alpha is not equal to alpha with an uppercase a. Both comparisons will give you a true result, and that makes sense. One, the top comparison is the same word. Obviously, they're the same. The second word is the same word, but it has a capital letter, so something is different. They are not the same. That makes sense. And we go down, and then they show you alpha is less than alphabet. That also makes sense. Alpha's got less letters than alphabet, so alphabet would probably be greater. Then at the bottom here is what I really wanted to concentrate on here. It says beta with a lowercase b is greater than beta with an uppercase b. Now, I don't know if it's common sense or not, but my logic in my brain says, well, the capital B should be weighted heavier than the lowercase b. So I would say that, just guessing without knowing anything, I would say that statement was false. The expression is actually true. And I wanted to just kind of go into why that is, because I don't think this module really explains why. Back in Module 3, we talked about bitwise operations, and I probably should have explained this then, but they kind of glossed over it, and we never went back. There were no labs on it, so I didn't elaborate. But here's where you start understanding the fundamentals of how the binary, the ones and zeros, are converted into the different computer languages, how the computer understands it based on how it's told to understand it. So in this this section, you were given the variable I and j. I is 15, j is 20, and then it says if these, each integer is stored with 32 bits, the bitwise image of these two variables will be as follows. So here we have I and j. I is 15, j is 22. Then here's the two 32-bit variables, what the 15 and the 22 are actually stored in the computer, because remember, computers speak binary. So everything's a conversion to a 1 and 0. Everything we do somehow converts to a 1 or a 0. To read, this is how you read binary, or this is how you convert everything from these 1s and 0s. You have to break these 32 bits into 4 sections or bytes of 8 bits. So 8 bits, there's 8 bits in a byte, and you make 4 of those out of those 32 bits. So we'll start with I. You got to break down these 8-bit sections into single bits to determine the value of each bit. And the way you do that is by creating this little table. This table goes from 1 and doubles each time. So 1 doubles to 2, doubles to 4, doubles to 8, doubles to 16, doubles to 32, 64, and 128. And I know that's a little weird because we read from left to right, but this is how it's done. I'm sorry, we read from right to left, and we're normally reading from left to right. So you can see here, let's say this first byte here, first 8 bits, it's all 0. So 0 plus 0 plus 0 plus 0 plus 0 equals 0. It's pretty simple. So generally we can just ignore the first 3 bytes and just focus on that last byte. So here we can see it maybe make a little more sense. You got zeros in the first 4, and then these are all 1s. Well, what does this mean? This means 8 plus 4 plus 2 equals 50, or plus 1 equals 15, right? 8, 4, 2, 1, and then that equals 15, and that's why I equals 15, or That's how that 15 is seen by the computer. Do the same thing with J. Break them down. The first ones are all 0. We know that. The last one has a bit in 16, has a 1 in 16, 0 and 8, and 0 and 1. When we add those numbers up, you get 22. That's why J equals 22. So back to section 5, and we look at the this bottom portion here, beta and beta. Lowercase beta is greater than uppercase beta, and again, intuitively, I would say that the big B is heavier than the little b. But this is why it's not. This is an ASCII chart, and on this chart you have decimal, the decimal representation, the hexadecimal representation, the octal, what character it is, or this could be a backspace, could be a tab. So if we look over the capital B here, the decimal is 66. The lowercase b here, the decimal is 98. This is why the little b is actually worth more than the big B, if that makes sense. It just comes on the list last, or after. The capitals come first, and then the lowercase list, which is the way I probably would have made the list. Just having the inverse effect. You put the capitals first because you think those are more important than, well, not really more important, but you get the idea. You would put the capitals first and then the lowercase. Well, that just ended up weighting these lowercases heavier. So when you're comparing strings, the ones with the lowercase letters are going to be different. Next video, we will go into Python, and I will show you how to use a little code to figure out what the binary, the decimal, hexadecimal, and all that stuff is for the strings as we compare them. Thanks.